Trusted OS communicates with the normal OS, and that has to go via EL3. And that code is very specific to the Trusted OS. There's no standard specifying how the EL3 code interacts with the Trusted OS. So we provided some interfaces to allow each Trusted OS vendor to create some specific code to provide that communications. And usually a Trusted OS would end up with a driver in the kernel and a library in the application layer. So Opti provides all of those 4 components. The 3 at the top are actually found in the Opti repository. The actual dispatch for Opti is part of the Trusted Firmware code base. The other part that Trusted Firmware requires is a port to a platform, and that's usually provided by the SoC vendor. And we have some interfaces for providing initialization and power management for the SoC vendors. The other aspect of Trusted Firmware is trying to provide at least a reference for a trusted board boot flow. So trusted board boot is a way of being able to ensure that the software that runs in trust zone is trustworthy, and it's tied back to a root of trust that is actually immutable on the platform. And at the same time trying to ensure that it's possible to update the firmware so that you can fix bugs and enhance the firmware over the life of a product. So this boot flow, the diagram here is actually for JUNO, which is not just got the application processors, but also happens to have an additional system control processor. So Trusted Firmware are the orange and red boxes in the middle. So you have a boot ROM, BL1, which would load and authenticate a actual bootloader, which runs in secure state, BL2, and that's responsible for finding and loading and authenticating all the remaining firmware that runs in secure state, which is BL3.1 and the actual trusted payload or Trusted OS kernel BL3.2 at the top. It also would be responsible for loading, authenticating the initial normal world bootloader, which is BL3.3 on the right. And if you have additional firmware on the device, one option is for that bootloader to also load and authenticate firmware for other processes on the system. Other boot flows are possible, and actually many other boot flows are possible, which still have the property of being able to authenticate the secure firmware and authenticate your initial normal world bootloader. But this is the flow that is actually present in our reference code. The project's open source at GitHub. It's a BSD license, and we accept contributions under a contribution license, which is very much the same as the Apache 2.0 contribution license. And last week we released our version 1.1, and the major additions really there was starting to add authentication. It's a prototype. There's a lot of work to be done on that to our trusted board boot flow. So we're actually starting to provide that authentication and trustworthiness. And there's a significant evolution around PSCI as a new specification was released last week. And I'll talk a bit more about that just now. And many and most of our partners who actually have ARM v8a platforms in development are using Trusted Firmware in one or more of their chips. So before we go a bit further, are there any questions about what Trusted Firmware is or where it fits into the software stack? Okay, well that's good. Just means we've been getting our message across. So just a little reminder of just this project is only 2 years old from when it was first actually had the idea that we should do something of this sort. So it was in February 2013 that actually first tracked down some discussions that we thought that this is probably might be a good idea. And before that, ARM had really stayed out of doing firmware. It was something that was really managed by individual SoC vendors, and the actual Trusted OS vendors had to then do their work on it. That took a few months to get to the point of having enough of an idea of what this would be and what we could do to actually sort of initiate some work on this. In June that year, we started talking to partners about it at Connect in July that year, and we finally got to an implementation which was provided to Linaro is binary form to put into the 64-bit open embedded builds that Linaro was creating at the time. And then finally, in October, so only 16 months ago, we released our first source code, and we had the first discussion about it at Connect. So in those 16 months, we found that we've got to the point where most of our partners are using the software for their V8 implementations. So there's still some questions about whether it works or whether it will fit in a particular system. And so the talk I gave a year ago, that was really focused around identifying and clarifying where it does work, and if it doesn't work, why you can still use it, or why we're prepared to change it to make it work for different systems. Lots of concerns that it wouldn't work with your own bootloaders, or because you have other software you need to run at EL3. Already by the middle of last year, the early adopters that we had working with us were starting to bring up trusted firmware on silicon. And in September last year, we released the JUNO port, and we also merged the Opti dispatcher during Connect. So that was a good high point. And now we've finally completed PSCI, or at least we thought we had, but we've got a new version of that specification. And the 96 boards, high keyboard, there's a port of ARM Trusted Firmware ongoing, and hopefully that will be contributed upstream when it's ready, or actually when it's running, and we can finish it later. So the two major features that we've got in the new release really are starting to work. We're starting to work on the trusted board boot. And I'll say starting to, because there's quite a bit to go, and it's not clear how far we'll go in terms of will we produce something that people will want to productize, or whether it will merely be a reference implementation of the specification. PSCI 1.0, so Charles isn't here to talk about that today, but he's done a lot of work in the last 4 months to actually add additional features and some clarifications to the specification. So I'll provide an introduction to what's in that specification. But that's available already at Info Center, and this time there's no click-through. It's a straight download. So trusted board boot. There's a specification from ARM, the trusted board boot requirements. At the moment it's still under NDA, but our security team have said that it's currently under review, and the plan is, subject to review, to be able to release that this quarter, so by the end of March. But it's not my responsibility, and I can't make promises on their behalf. So this talks about the requirements and how you meet the requirements coming from global platforms and from other areas in order to achieve a trustworthy boot, but be able to update and repair your firmware later on. So we have a prototype on our models and on JUNO. So this authenticates the images as part of the boot flow from the root of trust. In a reference implementation, rather than a fully optimized proprietary one, we are using X509 version 3 certificates, and the implementation is therefore there's more code, and it's a little bit larger than you might be able to do in an optimized version, but we're trying to keep it very clear as to what we're doing and how the chain of trust is established, and reduce the amount of space there is for security errors creeping in because we're using proprietary structures and techniques. So this is an optional part of the build for the BL1 and the BL2 parts of the boot chain. And right now we are using the Polar SSL cryptographic library, which has which has now been acquired by ARM, and this is now there was an announcement earlier in this week about this being sort of rebranded for the Mbed operating system, which is ARM's IoT operating system. However, the actual cryptographic library will still be provided on its own basis.
A question here for those of us who are not so into this. this BL1 and BL2, that's open firm, that's trusted firmware lingo, right? It means
Yes.
level 1, boot level 2.
Yeah, yeah. So the BL is stands for it's a bootload stage 1, bootload stage 2. To some extent, bootload stage 3 components, the actual runtime firmware that is in EL3, the trusted OS, and the normal world bootloaders are. The runtime firmware isn't really a bootloader stage because it's not doing any loading, but that's just terminology that's kind of like stuck over the last couple of years. The diagram here is actually showing you the actual cascade of the boot flow on JUNO. The green components are JUNO specific, although other platforms may have something similar. On the FEP, you can eliminate the green boxes and the flow then just runs through the orange and red ones. And it just shows the actual load and authentication activities, but also the flow of execution. I can walk through it if you're interested. The diagram in the top right is just an extract from the TBBR. It shows the actual certificate and key hierarchy that's specified now. TBBR is a specification that actually goes beyond just requirements, and it provides an example implementation, and we're trying to provide an implementation of that example. So it's not necessarily the only way to do this. It's just trying to provide one way that does provide meet the requirements. A comment about the use of Polar SSL. Today, Polar SSL has a GPL license, which is clearly not entirely compatible with the way some people want to build and provide firmware. There is there ARM plans to actually re-release Mbed TLS under an Apache license later this year. So we're using it in our reference code because it's a library that we expect in time to be one that we'd be happy to actually incorporate into our code base, and if people want to use the software for doing this functionality, that it'll be appropriate for this type of firmware. There is some changes needed to optimize and some of the Polar S algorithms for ARM v8 and for this software, but that's work for the future. So there's still some functionality missing from if you do for trusted boot. So we've got authenticated boot flow. We really need to implement firmware recovery. So if the boot fails, you need to have a mechanism for actually ensuring that you have a way of installing some updated firmware and then attempting to boot again. So, and there are additional optional features in TBBR, such as encrypting the images, binding the firmware to the platform, or supporting a trusted debug based on authentication certificates. The actual implementation is a prototype, and we have a fair bit of work to do on our interfaces and the actual structure of our design, because we want to provide flexibility in the right ways to replace the cryptography library, to actually be able to allow partners who want to use it to provide their own definitions and chains of trust. It's possible that they want to arrange the keys in a different hierarchy, to have additional keys in the chain, or potentially support additional keys for additional images on their own devices. And although alternatives won't match the example in the trusted board boot requirements, it's an improvement to provide flexibility in the framework that allows partners to implement the solutions that they want. And as I said, probably right towards the end of the year, we'll look more seriously at optimization of the code and data footprints. Are there any questions about trusted boot? I do know that most SSCs have their own.
I've got a question on the cryptography library. So you mentioned something about partners being able to have their own implementation. So is that something, can we actually use our own cryptography library instead of what is here?
That's definitely the intention. So I think the interfaces we've got on are probably not designed well for replacing it, and that's something we intend to tackle over the next quarter. So the idea is that you can use a different cryptography library, or you might be able to use hardware acceleration. and potentially entirely replace the entire authentication functionality with something that uses hardware support rather than software. Obviously, the reference implementation will be software, but we quite expect that that vendors will have either hardware accelerators or their preferred cryptography library code. So that's definitely one on our list of known requirements for this.
And is there an affinity to a particular bootloader in a sense? Does it work better with U-boot or UEFI or any? Is there?
No, this is trying to be neutral. So in terms of what is the non-trusted firmware and bootloader that's resident, we know it works. The software we've got works fine with any of them, and in terms of what happens with if you want to do secure boot in UEFI or verified boot in U-boot, part of the challenge there is deciding where you're going to store the keys for verifying the next stage of boot after that, and there are different approaches, and we aren't going to try and standardize that certainly within trusted firmware at this point, because it depends on the vendor and it depends on the product manufacturer as to how they want to approach that. Certainly, it's something that Linaro has had cards looking at doing those, at solving that. And in terms of where the storage for those keys and certificates is that still, I think, something that's discussed, but there's no implementation at the moment from Linaro. ARM Trusted Firmware will concern itself as far as authenticating that first normal world firmware image, but it's outside of the scope of the Trusted Firmware project to define how that gets taken further. So clearly it's something that we'd be happy to collaborate with the security working group and the other groups at Linaro who are working in that space as to making sure that they're providing appropriate solutions and actually being able to eventually demonstrate an end-to-end secure boot.
Andrew, as far as I know, the UEFI runs in EL2. In your diagram there, it's EL3, the non-trusted firmware. Does it mean that you should add UEFI in the picture, and there is a runtime library of the ARM Trusted Firmware?
That's probably just hard to read image because it's the resolution.
But thanks for posting the slides on the website.
Yes.
I'm looking at the slides.
So the non-trusted firmware is marked there as BL33, yes, which is bootloader stage 3.3. That's actually running according to the key at EL1, EL2. So the non-trusted firmware is not running at EL3. It's running at EL2, yes, although you can configure trusted firmware to run at EL1, yes, to run it at EL1. So it's it is running where it expects. Yeah, it's BL3. It's bootloader stage 3, not exception level 3. Yes, that the naming convention wasn't my idea, and it is potentially confusing if you're not so familiar with it. Have we got more questions about this? Yes.
Yeah. A question regarding the keys. So the key is possible to change it, like for example, the key maybe timestamp certificate, or maybe because of the key leak or something. What was the case of the changing of the key?
So the root of trust is usually expected to be something that is fixed in the hardware platform on the SoC. Depending on the market, it might actually be baked into the ROM, but it might be a one-time programmable fuse, and it's something that the actual OEM will program in. It depends on the market as to whether it's an SoC key, or whether that is the key that matches a private signing key belonging to the actual OEM. And that will vary between markets as to what's actually most appropriate. If that key is compromised, then yes, then all of the products with that key in are compromised. The chain of trust means that you only expect to use the root of trust key for signing the BL2 image and signing the firmware recovery images. You wouldn't and for signing the set of keys that are used for the next stage boot. So BL2 will basically verify what in the chain of trust here. Something like the normal world bootloader is signed by a key, which is in a certificate signed by a key which is used for the firmware stage 3 loaders, and that's signed by is in a certificate signed by the root of trust key. So that you have, you aren't using the root of trust key for signing all of the firmware, and you aren't using and possibly a key that is owned by the SoC manufacturer to sign the normal world bootloader. That actually there's a this chain of trust that provides that sort of an extra stage of key hierarchy, which means that the key that signs the bootloader for normal world might actually be one that belongs to a different organization or different part of the company. So obviously you would come up with an appropriate key hierarchy for the actual market and the product and the customer requirements. And so that's why we and that key hierarchy is something that you would have fixed in BL2 in terms of it would actually ensure that that policy is enforced. Because the expectation is that the firmware and the keys and the certificates, apart from the root of trust key, are probably stored in non-volatile, non-secure storage. But that because you have the root of trust with ROM code and the root of trust key, that you can actually verify that those are things that have been signed and authenticated to the manufacturer.
My question is related because I'm sort of asking who's watching the Watchman here. BL1, is that supposed to be sort of baked into the ROM?
Yes.
Yeah. Okay, that's how you do it.
Yeah.
You just put the program counter on it and it starts from there.
Yeah. So for this to work, you have to have a system where the application processor must start from a ROM address. So that anchors the root of trust into something that can't be changed. Other systems are possible. If you have a separate coprocessor which is actually doing the software boot, then obviously that might run from ROM, but it might do the authentication of the firmware, and it can actually, you could skip BL1 and BL2 on the application processor because the BL3.1 firmware is loaded and authenticated by some separate processor, which itself is part of the trusted domain. So
that's what JUNO does.
So JUNO does this. So I'll stand up and walk you through it here. So on JUNO, there's a separate system control processor for that does the power management control on the board, and it has a ROM, and the application processor also has a ROM. And the system control processor ROM essentially initializes enough of the system for the application processor to start. It starts the application processor. That runs its ROM code. I'll explain that it's not quite as what it seems on the JUNO in practice, but the design is to run the ROM code. That is BL1. It loads the BL2 image from NOR flash and authenticates it. The BL2 image then loads the actual runtime firmware for the control processor and authenticates it. And then there's a handover where that then gets installed on the SCP RAM and starts running. When that's actually initialized the DRAM and finished initializing the runtime firmware on the SCP, we do a handshake, and then BL2 carries on, and it now loads the rest of the images, which may be in SRAM and it may be in the DDR.
So BL2 has to be in SRAM?
Yes. Yeah. In terms of the actual trusted boot requirements, software that's running that's part of this trusted boot flow needs to run from secure memory. You can secure the DDR using some kind of address-based controller, but it's not really physically secure if it's off the chip. So the recommendation is you should try and run these stages from SRAM, and you should only authenticate data in SRAM rather than having it somewhere where it could be interfered with. Once you get to here, well, this might be in normal memory, but the point of the trusted boot is to be able to trust all of the secure software for running in trust zone. It might say, well, I can authenticate the normal world bootloader, but I'm not trusting it with the ability to look at what the secrets are that are protected by trust zone. So alternative flow, you might say, well, actually, this software is this is a processor that's capable of loading and authenticating this firmware because it's fast enough or it has acceleration, and you could do all of the firmware authentication over here on the control processor, and you ignore these boot stages and you jump straight into here in RAM, and you reset the application processor to RAM. But then this is clearly part of your trusted environment as well. So the gotcha on JUNO is the boot ROM predates trusted firmware. And so it's not quite compatible with trusted firmware, so we don't use the boot ROM on here. And on JUNO, the reset address of the application processor can be set by the SCP.
You put that as BL1 instead.
Yeah, so what happens is that BL1 is actually placed in flash memory, and the SCP boots the application processor into flash. So it's not actually, so it doesn't really meet the requirements of being a secure platform, but JUNO is designed to be a development platform, and we don't really want to start handing out the signing key to everybody. So although it does actually have a root of trust key fused into the board, we aren't going to start using that. For development purposes, then our boot ROM doesn't actually verify that the root of trust key matches anything on the hardware. It just says, yes, that root of trust key is fine. So if you actually start experimenting with this on JUNO FVP, you'll find that you can create your own keys and it all works, because there's no verification. One step further might be to actually embed the root key into our BL1 image, so that if you use the BL1 that you've created, you can guarantee that you have to be using the rest of the firmware you created, but it's still just a demonstration. Any more questions on this? Yes?
So in the U-boot case, that BL2 there would probably be the U-boot SPL then?
Sorry? In U-boot?
The U-boot SPL, the kind of mini U-boot.
Yeah, it can be SPL or it can be like the regular U-boots.
Well, this depends on how big your SRAM is.
I got the SRAM on the JUNO is big, so I put the entire U-boot.
You put it the whole thing in there, okay.
Yeah.
So we have a BL2 code in ARM Trusted Firmware, but as I said, we've designed trusted firmware, and particularly the earlier adopters. This is the bit that was really the missing piece, the BL3.1. So we focused the first year and a half on making sure that the BL3.1 was something that could be used to provide PSCI and integration with trusted OSs. And there are any number of solutions partners have for actually loading or authenticating BL3.1 in external processors or the application processor code. So sure, if you've got a trustworthy bootloader that you're running from in secure state and from SRAM, you could use that as part of the way of loading the rest of the firmware.
Yeah, I think, Kevin, to your question, you were asking about U-boot SPL. And if you're using U-boot with ARM Trusted Firmware, I don't think you'd be using the SPL stage at all.
Okay.
And it would be the blue box, the first blue box there. Once all of BL3, it would be the BL3.3 that it uses. It would have U-boot as the payload and off it goes. You don't need to have the SPL stage because most of the system is already set up.
The DRAM is available at that point, so
Okay.
it's set up by these other guys.
Yeah, I mean, you could in theory decide to try and run this from Flash or something, but then you haven't quite got the authentic. But the expected flow is that this has actually been loaded into RAM and authenticated in RAM, and therefore you've somewhere in the previous stages, either on a separate processor or possibly at this point, you've actually done the DDR initialization in BL2 so that it can start loading something large like UEFI or U-boot into DDR.
This actually simplifies our job a lot with well, actually both U-boot and UEFI, because there's less of that mucking about early startup.
So, I mean, if you have code that you usually would run in those early stages to do DRAM initialization, you'd migrate that into this bootloader.
So for trusted boot, UEFI must be signed as well, or
The expectation is that yes, this image, which is a part of the sort of like firmware package, is also signed. Yeah, obviously you could decide, look, in my chain of trust, I'm not going to sign it. Right? I'm only going to worry about authenticating the trusted firmware. But in a lot of systems, they're going, well, actually, I want to be able to then verify that I'm loading the kernel that I've created. And to be able to verify that, you have to load a bootloader that you know is your bootloader and will enforce your requirements on authenticating the kernel. Because if you break the chain of trust at one point, then someone just needs to put their own bootloader in their firmware, and then there's no guarantees of what happens afterwards. Another question?
How about the trusted debug case? Is the path any different than what we have seen here?
So the trusted debug case, I'd have to probably go and have a little reread again to remind me. But this is about debugging software in the secure state. In general, the idea is that part of the certificate hierarchy, there will be a certificate which actually describes what debugging facilities should be enabled or disabled on the hardware, because software running at EL3 is able to manipulate the debug capabilities of the hardware. So you can basically specify whether or not a debugger is able to access secure state. And you can do that by setting control bits on the CPU. And you would use a certificate there's a certificate containing that debug information. So you can update the firmware that would allow secure debug to be done, or a certain amount of secure debug, or you can make sure the firmware has a certificate that basically denies all debug capability from secure state. So the idea is actually, rather than wiring that into the firmware, you just would actually describe it in a certificate separately, which allows, it's easier to sort of provide an update, and you don't have to modify the firmware code to program the debug characteristics by changing code. So it's part of the specification. So hopefully that will be, when that's published, it's a bit easier to talk about this. More questions on Trusted Boot? Otherwise, I'll.
I have a question there.
Yes.
If the UEFI want to use the subkey to verify the latest image, for example, the color image, it can to use the Trusted Boot, the root key, to decrypt the subkey for the UEFI. There are various options if UEFI is trying to. So where does UEFI get the key for authenticating the kernel? One option is that the actual key is embedded in UEFI image. If it's going to actually extract it from elsewhere, then there is a question of how do you tie that back to the root of trust, or some root of trust on the device, something that you know that you're going to trust. So it would be possible to say, yeah, so you've got this key hierarchy, you can basically extend it and add additional entries on that chain of keys. Obviously UEFI would need to verify that key chain all the way back to the root itself, because it's going to be extracting certificates and keys from non-secure, non-volatile memories, and so we'll have to establish that chain of trust by finding a chain of keys that goes back to that trusted root. You might need to have some kind of interface to the secure world to actually give you what the root of trust key is. But of course, it's because it's a public signing, it's a public key or a hash of it. It's not a security breach to say here's the root of trust key. Or there might be an interface to say, is this true? Can I use this key? Because there are a number of different options for this, I don't think the discussions about key storage and secure storage for extracting keys for UEFI hasn't quite resolved itself at Linaro yet, because it's not, there's not a consensus as to exactly what's the right reference implementation to demonstrate, because there are different approaches.
Well, actually, UEFI has its own root key, right? So, and the spec.
Is that normal? Is that something that is actually embedded into the UEFI binary, or is it the implementer's choice as to where they find that?
It's implemented as being a secure variable in the variables one.
Right. So it's up to the implementer to decide what to.
How your secure storage is actually implemented, and it might in some way tie that into something else in secure firmware. But from UEFI's point of view, it just starts at the platform key, the PK, and that's where everything else is built on top of.
So holistically, it would make sense to look at the key hierarchy that you've established for the trusted world and say, right now, where do I hang off my normal world keys, and tie it all back to that root of trust key.
Sorry,
JUNO as some SoC vendor already provided the security boot or the authenticated boot. So what's the difference between this and that? Is there any interaction between the boot room and this trusted firmware?
So, is the question, so SoC vendors who have got V8 hardware and have implemented authenticated boot.
Yeah.
So, the difference here is that we want to provide some reference code that people can look at and play with. If partners actually implemented, a member's got a secure boot running on their V8 platform, they're not going to let you play with their secure boot solution. They probably won't let you modify the firmware on it. And so if you want to actually explore trusted secure boot and explore and basically have some way of verifying whether that works and being able to demonstrate it, you need some an implementation that's open that you can actually manipulate and experiment with. So this is something that should just work once you've decided how to tie it onto the platform, if at all, with the high keyboard once that port is available, and it gives you an ability to act as open source that you can actually experiment with a reference implementation. It may not actually be in a product. It may be similar but not the same as what you find in SoCs. There's no requirement that a member decides to use this software in their platform. But the software that goes into members' platforms isn't one that we can, in general, experiment with.
So does it require ARM V8 or is it available on ARM V7 as well?
Trusted firmware only runs on 64-bit ARM V8 today.
What's the possibility of getting it running on V7?
There's probably a fair amount of work involved because of the architecture is quite different, and probably some software architectural decisions that would need to be made around image structure, because the monitor and the trusted OS are hard to separate on V7. So it would likely look different, and it would be the challenge is really identifying the amount of value you'd get out of it, because it's already highly fragmented, and it's not just like defragmenting the CPU idle space that Lorenzo was talking about yesterday. It's about you defragmenting the trusted OS space, and they've all got established solutions. So there might be some incremental steps that would be interesting to explore, like providing a standard PSCI library that can be integrated, but actually doing a full port is not currently in our plans. It's certainly on our radar, but not something we're planning on right now. I want to spend the last 5 minutes at least just to provide a quick look at power state coordinate interface. The full specification is actually at Info Center, as I said. There's been lots of work discussing this. It's not just the last 4 months. That's been the review cycle with the draft. It's been over the last year. Discussions with OS vendors and silicon vendors. It's aligned with device tree and ACPI. The migration from 0.2 is quite simple. It's pretty much compatible. Certainly the 0.2 kernel drive, CPU idle drives and hot plug drivers work with a minimal 1.0 implementation, which is what we have in GitHub right now. There's lots of optional features, and we'll be working on implementing those through this year. This gives an outline of the changes, which is a bit shorter than reading the whole document. One of the things in PSCI 1.0 was 0.2. There was a model of how power domains, and they were very tightly coupled with affinity levels. And that works for many systems, but as soon as you have a system where a cluster of, say, 4 cores hasn't got a uniform sort of structure with all 4 cores having their own cache and tying into a sort of shared cache, but if you put intermediate caches in that maybe has pairs of cores with an intermediate level cache, you'd like to model that in your power domain, because that cache might want to be put into retention or power off states. So you want a power domain hierarchy that's a little bit more detailed than what you can find in the affinity hierarchy, which would describe cores and clusters and systems. So removing that assumption and providing more flexibility in the topology allows better match to hardware and opportunities for better optimization in terms of low power states. There's some improvements in the diagnostics. So
at the moment you can ask what the state of any particular part of the hierarchy is, but it's actually the state that PSCI thinks it's in, not necessarily the physical state. So we've added something to actually interrogate what the physical state of any part of the system is. And there's some optional metrics for instrumentation to actually calculate, work out how much time has been spent in various low power states. So in terms of actually measuring how the system is behaving in use cases, this will help when we have, for those purposes. A slightly more sort of interesting evolution.
Andrew, what do you do with that information? Once you collect it, how much time you spend on each state? What do you do with that?
It's more it's useful from a point of view is if you're doing the platform port and you're expecting that you're going to find yourself in retention or low power states on cores and clusters, or you'd like it to be in lower power states for a certain proportion of the time for a use case. This can give you some statistics on exactly how much time you did spend there. So I'll use my voice.
So that means I have to instrument my EL3 code to do something with that?
Yeah, so our implementation will basically have a build option that will build in the statistics.
Okay.
So you basically turn this on in your build of the EL3 firmware, and then you can extract the statistics. So there's no, so our intention is to make it basically part of the generic implementation. So OS initiated mode is a slightly interesting one. At the moment, the whole design of PSCI was each CPU votes what it wants. The platform firmware decides what's possible based on. So if a CPU says that I don't want to go below CPU power down because of the latency of wake up, then any other CPUs, if they say, well, I'm quite happy to turn off the cluster won't power down because one of the CPUs says I'm not prepared to have the cluster power off. And only if all of the CPUs essentially vote to say that the cluster can power off within the cluster, will the cluster itself power off. This works fine for CPU power management. The interaction with runtime PM and when peripherals start having sort of voting rights on keeping certain parts of the hardware awake means that CPUs may not opt for as low power state as that you could eventually achieve, because there's a peripheral. When the CPU goes idle, the peripheral itself is preventing the CPU from a deeper sleep state. Once the peripheral requirement is relaxed and no longer requires the hardware resource, runtime PM wakes everybody up, and then everybody has another chance at having a vote on actually how deep a sleep they want to go into. So that is somewhat inefficient, and exactly how inefficient depends on the system and the platform. One solution is to push some of that logic down into the firmware and actually have the peripheral voting being done by the firmware rather than in Linux. Another solution is to actually, in the OS initiated mode, is a different approach which says that instead of allowing the firmware to work out the result of all the voting, is that the OS gives a precise request that says put these parts of the hierarchy into this state. If you can't achieve that state, then fail the request. And in that situation, the OS knows what it thinks this system it thinks it is in, and it means that the last CPU in a cluster can actually turn the cluster off, even if the other CPUs at the time they turned off couldn't have done. So it allows it would allow the OS to basically take explicit control of all the levels in the power hierarchy. That would require changes to the drivers in Linux and the frameworks in Linux to actually exploit it. But it's certainly something that it's a way some other operating systems work, and it's something that could be done if that actually provides power advantages in Linux. It's something that might be explored later in terms of Linux. Certainly, you might see point solutions from some partners who find that can work. So that's really a trade-off between whether you have more complex firmware to manage this or more complex operating system software. And given that we don't want to dictate which choices is made, that's the PSCI has basically said, right, we're going to make it possible to have the operating system make that choice. And something that certainly ARM was pursuing was a spenter RAM, which is rather than having to find out what the power state parameter for being able to basically turn everything except the RAM off, there's a call for doing a suspend to RAM for the system. I think that's everything I had in my slide deck. So one thing I'm not sure what's going to happen. I'm thinking it might get easier to start experimenting with trusted firmware software where you're not having to just run it on a model, because I'm certainly encouraging the 96 boards platforms to port ARM Trusted Firmware and upstream the ports to our GitHub repository, which makes it easier for everybody to run this code on real hardware. JUNO is not that available.
Is there a certification, like if an OEM or software vendor were to be, if they claim that they have trusted firmware, is there a way for ARM or to have to certify that they're indeed running trusted firmware, meeting the requirements of the specification?
There isn't at the moment. I don't think we see a need for that. There might be. You might say it might be interesting to know whether you can actually declare compliance for PSCI. Trusted firmware itself is trying to be available as a portable framework or just a source of certain bits of implementation that you'd like to use in your own firmware. We don't want to dictate how it gets used. At this point, we want it just to get used. Maybe in time.
But there'll probably be an issue with OEMs or software vendors, right? Especially when they try to indemnify, companies against any issues that crop up. They may want to have their solution, right, and not use another solution. That could be, for example, you could have a solution like this, and someone could, say, like report bugs on the internet about things, ways to hack this in, and that may not be, something that they would readily embrace. So, which is why I brought that subject up.
Yeah. So one thing that we are looking at this year is that because of the rapid adoption rate of the software, is looking at putting in place things around vulnerability reporting, because it starts looking quite attractive as a software to explore for vulnerabilities. Ultimately, it's going to be the SoC vendors and the OEM vendors who have to make sure that the software they deploy is secure. But we obviously want to play our part in ensuring that we're not, leaving the door open and making it hard to close for those partners.
Yeah. If I can also weigh in on that, from a platform point of view, with LEG, we're wanting to see ARM Trusted Firmware, but it's not something that's actually visible to the applications, to the operating system and the application stack. This, well, you don't have the diagram up there, but all of this ends up being internal detail for how the firmware is implemented. But when we're looking for what makes the platform, like for enterprise, it's very much what is the interface that we're seeing. So PSCI, we're going to want to do testing for PSCI, and what I would like to see is we've done a lot of that work for enterprise. There's going to be some bleed out. I'd like to be doing the same sort of testing for the other market areas.
So is there any thought in ARM Trusted Firmware expanding to standardize some error reporting for like RAS? There are some system errors that are going to be handled in a secure state. So any thoughts on sort of how that would fit with ARM Trusted Firmware? Is there some opportunities for some standardization there?
So just to repeat the question, so this is a question about whether standardization around some areas of RAS, where particularly it's actually going to happen on the CPU core, is worth pursuing. It's certainly a topic that is being discussed at ARM. Standardization could be useful because not all errors are going to surface can actually be handled on an independent processor, which is perhaps a more reliable way to handle it. Some of them will surface at EL3 on the processor itself. I know some partners have been implementing some of this stuff themselves, and standardization would probably be a valuable exercise. So there is some ongoing discussions about how to start doing that in a similar way to PSCI has provided a standard interface for supporting that. But it's sort of early days in terms of where that's at. So it's not going unnoticed. Is about the sort of strongest I can commit to that set comment on that right now.
Good question.
Sorry?
Good question.
Right, so we're 5 minutes over. Thanks for all the good questions, and the slides are already on with the session. And as we say here, we really would like your feedback on the software and the current state of the project, and whether you send us that feedback on GitHub or whether you email it to us. Feedback is appreciated. Contributions are always welcome. Okay, thank you.